Welcome and good afternoon. This is the third webinar from the AusGeochem Geochemistry Network. My name is Brent McInnes. I'm the coordinator of the AusGeochem Earth Composition and Evolution Program. I'm also the director of the John Delator Center at Curtin University. I'll be your initial host today for the webinar, which features the research team from Macquarie University. Before we begin, I'd like to acknowledge the traditional owners of the land on which we meet. In my case, here at Curtin University, they are the Whadjuk people, while the Macquarie team acknowledges the traditional owners of their land as the Watamatical clan of the Darug Nation. Collectively, we recognize their continuing connection to land, waters, and culture, and pay respects to their elders, past, present, and emerging. The AusGeochem Geochemistry Network, or the AGN, is part of the National Collaborative Research Infrastructure Strategy and was established to address a community-wide desire for an increased level of cooperation and coordination between Australian geochemistry research laboratories. A key objective for the AGN project is to build and operate a national geochemical open data repository called AusGeochem. And we have teamed up with Melbourne-based SME Lithodat to deliver the required online data platform. The AGN also has a role in promoting the professional development of research facility staff, coordinating research infrastructure investment on a national scale, and facilitating improved end-user access to AGN facilities. I'm pleased to report a brief report on the last activities in the last 6 weeks. We have produced 2 websites which provide detailed information on the AGN and on AusGeochem specifically. There you will find a link to all presentations that have been made on AGN via our YouTube channel. We've also submitted 2 funding proposals, one to the Australian Data Partnerships Program of the Australian Research Data Commons group. That proposal is to create AGN Plus, which will take the number of nodes that are in AGN from 3 up to 10, and that's the image on the right-hand side. There's also a proposal led by Tim Rawling, and that is in the data platforms area, and that is about getting data off machines and into data repositories. The outcomes for those 2 proposals are expected next month. I also can report on successful participation in eResearch Australia by Sam Boone and Eleanor Bellero. That conference was held last week. We're currently lining up the next webinar presentation, which is tentatively scheduled for the 9th of December. So we may call upon various groups to participate in the next webinar. Without further ado, let's get to the main event today, which is a presentation by Sue O'Reilly, Olivia Allard, Elena Belasova, Joanne Gros, Guillaume Florin, and Lauren Gorojovsky. I'll hand over to Sue. Thank you.
Welcome, everybody. It's great to see a whole lot of familiar faces who've tuned in, so that's a wide variety of audience. It's wonderful to have this opportunity to talk to you about Macquarie's TerraneChron tool. It's a geochemical remote sensing technique, and it was enabled by many developments in technology and methodologies, and it was very much informed by industry collaborators. There are many benchmarks that have either helped to establish it or to improve it along the way. The first benchmark was the ability to analyse trace elements of minerals in situ, and some of you probably can't remember when we couldn't do that. That started with the Electron Microprobe in 1988 and then proceeded with others to the laser ablation ICP-MS in 1996, and that enabled analysis with spatial resolution for trace elements, just as previously we had been able to do that for major elements with the Electron Microprobe. The second benchmark was to develop an analysis in situ method for hafnium isotopes. And when we published that first paper, just 3 months after our first multi-collector arrived in 2000, we more than 10 times increased the number of analyses of hafnium in zircon in the whole literature that had gone previously, which was a testament to the rapid and effective way that in situ analysis could be done. We then were able to combine zircon trace elements, uranium-lead geochronology, and hafnium isotopes, with hafnium bringing enormous value add to the simple geochronology information that uranium-lead could tell us. This then enabled applications such as being able to track the Earth's crustal evolution, and that is a fundamental research application. It was also a valuable evaluation tool and very much used by the exploration industry for minerals and for energy resources, and particularly in estimating the metallogenic potential of defined geologic terranes. More recently, as we get larger and larger data sets, we've been able to show it's a proxy for paleogeophysics, and also with large data sets for isotopic mapping at regional scales. Not only is that isotopic mapping possible for across the surface, but we can do it mid-crust and lower crustal levels because of that value-add information given by hafnium isotopes. The third benchmark was the development of in situ rhenium osmium analyses in mantle sulfides, giving for the first time an ability to date mantle events accurately. That was in 2002, and we owe that to Olivier Allard here when he was a PhD student. The combination of rhenium osmium with the hafnium isotopes enabled understanding or better understanding of crust mantle evolution, because we had the whole lithosphere section with which we could apply those techniques. This fitted in very well with the overarching vision of CCFS and GEMOC, which is delivering the fundamental science needed to sustain Australia's resource base. To do this, it required that we were able to track the evolution of deep crust and lithosphere terranes, to define geochemical and geophysical regions within the lithosphere, and particularly within the mantle, and to give the timing of such things as the processes and events that affected asthenosphere and lithosphere interaction. This enabled us to understand how economic deposits are formed, where they're formed, how they're formed, when they're formed, on the scale of ore systems, which is actually the lithosphere scale. One very neat application is evidenced by this study that we did based on zircons in xenoliths brought up by kimberlite diatremes in the southern North China Craton. The mid-crustal region there was the first crust formed in the Archean 3.5 billion years. That was resurfaced at 2.8. So if we just map the surface, we will get an age of 2.8 for that terrain. But it was actually formed in the Archean. It was then underplated twice, once by 1.9 billion material and then by 1.8 billion material, adding to the crustal mass at the base and lowering the moho. These events actually coincide directly with events that are mapped in tectonic terranes at the surface, and they are the collisions of the east and west North China Craton with Pangaea at about 2 billion years, the Yangtze and North China Craton at 440, which is the Qingling origin, and the Dabi Sulu origin at 240 million years. As we went on, there were different ways of presenting the data for isotopic mapping, and of course the first diagram there is the one that is used in academic publications. Our industry partners really like the event signature because it's an easy way to image events that happen. Trails that go upwards indicate mantle input, juvenile material coming in, and tracks that go downwards are crustal reworking. And the mineralisation events in both of those, when those two terranes docked after being very separate, they're like paleomagnetic wander paths, the mineralisation is due to mantle input, juvenile mantle input, at about the same time in the Mount Isa and the Broken Hill blocks. The early data that we did on the Zircon block, you'll see a more recent data in a moment, showed that the western part is very old with epsilon hafnium less than 0, and the eastern part much younger with epsilon greater than 0, and that's a very granular interpretation of the age of terranes within that belt. A very nice example of isotopic mapping was done by David Moll within CCFS, and this shows the Yilgarn. I'm just going to concentrate on this part, which is the craton margin at 2.8 million years. At that time, the Yilgarn was simply that left-hand bit, and then it was docked with this other terrane at 2.6 to 2.7 billion years, and you can see that these highlighted areas of mineralisation are associated with the processes that occur at those craton margins. So that's a really critical aspect. Another place where isotopic mapping shows us this relationship of mantle and ore deposition is in the Lhasa block of the Tibet terrane, where we have very rich porphyry copper gold deposits, and they can be associated with upwelling material. We have a tomographic surface here at about 100 kilometres, upwelling material, and here we can see it in cross-section. So again, the hafnium isotope data, which we have on a colour scale here, give us an indication of the information that we can get about their origin. And I think probably the most important thing we've done, the biggest result that we've had, which is like an umbrella over all the rest, is to show that 70% of all the continental regions, shown in black here, actually have Archean origins. So the cratons throughout time haven't been destroyed and very little creation has happened. They've been rearranged. And that's also really important for looking at economic deposit location. And now I'll hand over to Olivier Lard, who will tell us how we do the analyses for these particular applications.
I am Olivier Allard. I am the director of MQGA. And as we all know, I mean, the TerraneChron and the AGN database will feed on a high volume of high quality data. And reliable geochemical data require EV structures, EV infrastructure, and hard-scale people. And here is the team that we have here working at MQGA. So the MQGA is an integrated facility, partly supported by AusGeochem and Chris, and therefore we are welcoming any request, analytical request, collaboration from the industry, government agency, and academic researchers. So the MQGA has been built thanks to the relentless effort of Sue, Bill, and Norm, and other MQ researchers, and to the generous support of various funding bodies, which are represented on the bottom of the slides. But also, I mean, MQGA, at the core of MQGA, analytical is the analytical development. And these analytical development were only possible because we were strongly supported by the industry manufacturer, such as New Plasma, Thermo, Chemica, Agilent, Teledyne, and so on. So one infrastructure which is often overlooked is the sample preparation. And indeed, without careful and skilled sample preparation, none of the data, the high-tech data, will be possible. So at Macquarie, we have an extensive lab with an extensive range of machines and instruments, allowing us to process rocks from the field down to the minute minerals that we will work in. And Johan will give more detail about this process later on. So high-tech isotopic data needs to be interpreted within a well-documented petrological and geochemical framework. And for that, we have a range of machines able to characterize the chemistry and the mineralogy of rocks at various scales, so like the micro X-ray scanner or the classic scanning electron microscope, but also high-resolution FEG SEM that we call nanomin, which allow us to characterize the chemistry and the mineralogy of nanophase, which we believe are the next target of exploration geochemistry. Of course, we need the concentration of major elements of minerals, and for that we rely on our old but faithful electron microprobes, the workhorse of the labs. And with this data, we can go to the next step, going to the in situ trace elements and isotopic data. So mostly the MQGA is known for its work on plasma mass spectrometry, and over the years we have developed a number of laser ablation ICP-MS and laser ablation multi-collector ICP-MS techniques, and that for a variety of matrix and application. We are also home of the glitter package, and Lauren will give a bit more information about it at the end, as we are planning to put soon a new version of glitter out. So yes, we do have a lot of ICP-MS and multi-collector ICP-MS. It would be too long to go through one by one, but let's say that we have the mass spectrometer to answer your questions. In situ trace element analysis in silicate is nowadays pretty routine. However, if you spice up a bit your plasma, then you can increase your sensitivity, and you are able to explore the low ppb level or infra ppb level, and that open new avenue of research, such as using olivine as a mineral tracer, or using siderophile and chalcophile ultra trace element in silicate as a geochemical tracer. In terms of data quality, we are basically bang on the money, and we in fact define the trend as it is shown here by the various round robin testing, and even so in the unconventional, or let's say tougher to analyze elements. Since a couple of years, we have invested a lot of times in the development of trace element imaging, especially led by AGN and in collaboration with Teledyne. And here, for example, is a cow teeth from archaeological dig in Sydney. And this study, along with correlative strontium isotopes, shows that at the beginning of the settlement in Sydney, the cow were imported directly from England and didn't have much time to enjoy Australian grazing before being transformed in steak. So one of the pillars of the TerraneChron methodology is the possibility to acquire fast, cost-effective, accurate uranium-lead analysis on zircon by laser ICP-MS analysis. We pioneer this technique in Australia, and we also develop a number of reference material like the JJ Zircons, but now the MT Zircons. Again, the international round robin shows that MQGA, which is here, is one of the best labs in the world for such kind of techniques. And later on, Elena will talk about the developments that we are doing in uranium lead about monazite, apatite, and rutile. Okay, so one of the recent additions to our analytical park was the QQQ ICP-MS, and we have a lot of fun with it. And for instance, that technology allows us to revisit the rubidium strontium geochronology, but this time in situ. And I believe that this new technique will be a very good addition to, a very important addition to the TerraneChron methodology. And Lauren here will present a bit more about that at the end of this presentation. Okay, so with this QQQ, we can also look at sulfur, selenium, tellurium, and copper. And these three elements are very important for carbon-free technology. However, selenium and tellurium are very rare, and copper is in such a high demand that we will have soon to be really worried about the supply. So here it's a study which will shows that we can now in situ analyze selenium and tellurium at the ppb level, And we see as a preliminary results that tellurium and copper are behaving in subduction magma as model, but not selenium and tellurium, which basically suggests that, yes, selenium and tellurium are very good tracer of the chalcophile, chalcophile mat, but we still have a lot of to understand on the behavior of these elements and on the information that they carry about metal movement in the deep earth. Moving to the isotopic side of the MQGA, we have indeed two Triton TIMS mass spectrometer, allowing us to measure very precisely isotope of the raw rock, and like that we can relate it to the in situ data that we obtain, and those teams are looked after by Peter. So we have also a very talented team of postdocs working on the Neptune Plus in the thermo hub, and they have developed a number of applications using what we call non-traditional isotopes of various affinities from siderophile to chalcophile. I invite you to look at the publication. Let's go to the now laser multi-collector ICP-MS new plasma, where we get the hafnium data, which are the second key part of the TerraneChron methodology. And on those instruments, we are also developing new applications like hafnium isotope in low hafnium minerals with on rutile, and also AGN is developing zirconium isotopes in zircons. Recently, we have upgraded our plasma with a range of detector, allowing a bit more dynamic and flexibility, which alleviates some of the analytical limitations that we had, for example, with these new laser splitting techniques, which allow us to measure on one single shot osmium isotopes and a full pattern of PGEs for tiny sulfide inclusions. And that basically gives you a better way of interpreting your data. And for us, that is representative of the future of geochemistry, which is basically you need to acquire a dense, rich, and variable matrix of chemical data on a single point, either using correlative in situ isotopic composition or basically by doing splitting systems. And now I will leave the screen or the seat to Johan, who is our specialist of multi-collector ICP-MS and has a long experience in the TerraneChron methodology.
Hi, everyone. As Olivier said, my name is Johan Greau, and I will take you through the concept behind TerraneChron, the sampling strategies, and how we acquire the data. So first of all, the TerraneChron concept is based on the integrated in situ analysis of zircons for uranium-lead isotopes, lutetium-hafnium isotopes, and trace elements concentration. These will be used to understand the crustal evolution and evaluate the metallogenic potential of terranes. So the main motivations behind this concept is a region with a lack of outcrop, which can significantly increase the cost of exploration. This is the case, obviously, for Australia, but also in regions with very densely forested and mountainous areas, like Indonesia or PNG. You may also have an outcrop, but not necessarily a geological framework to relate it to, and it is the case in greenfield exploration, for example. So to circumvent these problems, we use zircons. So zircons are very resilient minerals, both chemically and mechanically, which means that they will be retrieved even a long time after the host rock has been weathered away. They also possess a very amazing set of chemical elements in their composition, making them pretty much real-life time capsules. So using uranium-lead isotopes, for example, you can get the age of magma. Using trace elements, you will get the type of magma. And using lutetium-hafnium isotopes, you will be able to know the source, either a crustal source or a mantle source. And also using lutetium-hafnium isotopes, you will be able to get an estimate on the age of this source. So in terms of sampling strategy, there is the single rock approach, which is the traditional exploration method. It's excellent to date single rocks or small structures, but it is time and dollar intensive when it comes to large terrain. Or you can use zircons from drainage sample within a defined catchment. So basically, if you sample a few strategic streams, you can basically do remote sensing of a large and geologically complex area. And here we've got the two examples of two catchments in northwestern Australia. So once you have your samples, you need to recover the zircons, obviously. So if you have a rock, we'll start with a self-frag technique, which is a selective electrodynamic fragmentation of the rock using a high voltage. This technique has the advantage to limit contamination, limit broken grains, and generates high yield. We will move then onto magnetic separation using friends, and then onto heavy liquid separation. Once you have the zircons, you need to handpick them and mount them on epoxy mount, which will be polished for further analytical work. The third step, which is the first analytical step per se, involves electron-beam techniques. So all our zircons will be going through cathodoluminescence imaging using SEM. We do this to identify the internal growth pattern of the zircons. So here you've got a set of CL images of zircons. And if you look at the one on the right, you can see a very distinct core and rim structure. And Elena will talk about this specific sample a bit later on. And obviously, we also acquire major element composition using laser microprobe. Then we move on to step 4, which is the in situ uranium lead dating, which is very much at the core of the TerraneChron methodology. So we use laser ablation ICP-MS to measure uranium, lead, and thorium isotopes, but also trace elements simultaneously. And then we reduce the data using our glitter software. So here you've got a screenshot of the glitter software with the ablation signal on the top right, the zircon trace element patterns on the bottom right, and the uranium lead Concordia edges on the bottom left. And then last but not least, the in situ lutetium hafnium isotopes. So this time they're acquired using laser ablation multi-collector ICP-MS. So here you can see some very nice zircons about to be ablated for the second time. They will go through our new instrument multi-collector ICP-MS. The data will then again be reduced in a time-resolved fashion. And then the data will be sent for interpretation and to data interpretation with our expert. And I think this is it for me. So without saying anything else, I will leave you with our most prominent expert, Elena Belousova.
Thank you so much, Johan. So my name is Elena Belousova, and I will be talking about our TerraneChron approach and some application we had in the past. So certainly TerraneChron is aiming our end users mineral industry. Direct their successful exploration strategies. But I would also point out that the amount of the data we collect on zircons allow us to address a range of geological applications. Some of them are listed here. And most importantly, they are not restricted just to provenance studies and not limited to just to detrital zircons. So on our way to develop this technique and leading to TerraneChron, we made some large impact outcomes. And some of these publications are world benchmarks. And you can see this is really reflected in the number of citations this paper received over the years. It's also allowed us not only connect with the exploration industry, but attract quite a number of collaboration, not only national, but also international. And that allow us to create an enormous amount of interactive projects, and which resulted in a significant number of TerraneChron related publications and reports. Well, I would like to show you a couple of examples of this collaborative work. This study was done in collaboration with the Geological Survey of South Australia. And the question was to look in this relatively small inlier, Houghton inlier, where the Geological Survey knew this Proterozoic inlier has the ages quite similar to those known in Angola Craton, but also in the Cunamuna province. So we just sample a little river which is draining the Houghton inlier. I'm not quite sure if it's visible or covered. And this sample by panning, so we could extract quite a number of the useful grains for analysis. And we found out that there are clearly two major populations. One is igneous and one is clearly metamorphic overgrowth, two populations. But however, this age alone could not resolve our questions because both of these crustal blocks have recorded the same event. However, obviously in the Houghton grains, they're sitting really close to the Gola craton and unfortunately lacking this important juvenile input, which is known for the broken hill area and most likely a key factor for this economic potential of this crustal block. Another example, it was part of the PhD study by our PhD student, Irina Tretiakova. And we were lucky with the samples of the kimberlites provided by Alrosa. And the kimberlite in Siberian Craton sampling across this huge cratonic area over 1,000 kilometers. So we had not only the sample representing across the continental crust, but also through the upper mantle. And having this information, we could look at the entire evolution of this Siberian lithosphere, with the earliest crust formation event recorded as early as 3.3, 3.6, or possibly early, with some Archean grains having this negative epsilon hafnium values, indicating that the protholis probably much older than that. The next event was a major crust formation event happening at 2.7 billion years. After that, we can see a period where this original crust was reworked until around 1.9 million years, when we again see some addition of juvenile material and a new addition to the crust, and also a significant amount of the reworking of this older pre-existing crust. And this event is well known in Siberia and was interpreted as the major event of the final assembly of this craton. And then very little happening around the craton until the Phanerozoic time, when we have a kimberlite emplacement across the craton. If we look at even larger scale application, this is very well illustrated by our study for the crustal evolution on a global scale. After probably 8 or 9 years of our work with all the collaboration with industry and research institution, we collected quite a significant database. And then we realized this database are really not restricted to single continent. So here the data is color-coded by continent. And you can see that we could really do a global application where we can identify these grains and events which are plotting closer to depleted mantle evolution line and allow us to build up this growth curve, which and allow us estimates of the rates of the continental crust growth through time. And our conclusions are that at least 70% of the continental crust was formed by the end of the Archean time. So just a few words about our intentions for future. We think that our future is a multi-proxy approach, when we're not only focusing on zircons, but other uranium-containing minerals for higher resolution and geochemical remote sensing to capture a more complete geological history, where they can extend it to low temperature event, metasomatic, metamorphic, hydrothermal event. We also can build up a thermal history of the rocks using the range of those minerals with different closure temperatures. And we can advance our provenance study as well as advance our exploration, having a better identification of these vectors towards diverse exploration targets. Thank you so much, and I will pass the screen now to Guillaume, and he will be talking about the data management at Macquarie University. Thank you.
Okay. Hello, everyone. I'm Guillaume Florent, AGN data scientist for Macquarie University. And I'm going to talk a bit more about the technical part of data curation at Macquarie University and of the future of data curation. So, as previously said, TerraneChron and GeoMock provide facilities for researcher and industry to do some analysis and interpretation under AusGeochem agreements. Since their creation, more than 20,000 samples were analyzed by LAMC ICP-MS. All through data stored in Macquarie archive and in some published paper, some data remains confidential due to industry agreement or individual researcher financement. It is also pretty complex to gain permission to put them online and to have, for example, all the metadata associated to each sample, such as GPS location, etc. So there is a need to systematize data curation, data analysis for legacy curation. To do that, we are developing a lutetium, hafnium, and uranium lead database, and we are working with an expert group composed of the different people that you can see here. So the goal of that database is to allow a proper curation of past, current, and future data. You have here an example of one of the tables of the lutetium hafnium database, which is linked to a minimum metadata table. As I told you, this table sums up the entire important data, such as how a sample has been analyzed or the GPS location of the sample. But this is going to be developed in the next webinar. So we are now populating the database from the AGN nodes and from some individual database. But soon you will be able to do your analysis at Macquarie University and work on it from all over the world. To do that, we are developing an API, which is software which aims to auto-populate the database during your analysis. And it's going to associate it to each sample and AGSN, which is going to help for legacy curation of your sample. After your analysis, your data will be georeferenced online on the AusGeochem GeoChem platform, and you will be able to select and work on your data directly online. So here you have an example of some lutetium hafnium data plotted on a map near from Sydney. You will also be able to compare your data with the entire database, and this is the power of this kind of platform. You have, for example, here some uranium, lead, or rubidium strontium data. After selecting your data, you will be able to work on your data online and create some diagram, for example, like Terra-Weatherberg plots, or some hafnium versus age plots, or some density plot. This is only some example, and much more will be possible. We are at the moment developing and working with the expert group on the possibility of the database. So finally, you would be able to add your diagram in one dashboard along with your data to export them and share them. All the graphic that you will have added or on your dashboard will have a drop-down menu, so you will be able to change them directly on the fly. After that, you will be able to export that directly on your computer for more convenience. But that's not all. After processing the data, and you will be able to share your data, your plot, and to manage the privacy of your unpublished data. So it's going to be a workplace to share with other collaborators working on the same project. Finally, our goal is to save data for legacy creation. Because high-grade data need high-quality storage, GEMOC and TerraneChron take part to the AusGeochem Geochemistry Network project. We are developing a database which aims to be simple and auto-populated, a database that is going to be accessible online on the AusGeochem Geochemistry Network platform. It's going to be a working place to share your data with your network, but also a powerful space in which you will be able to compare your data with decades of previous data. A multitask place to do your online reduction and data visualization, and all of that for legacy creation. So I will now let Lauren, the PhD student of Olivier Allard, speak more about advanced and new developments. Thank you for your attention.
Hello, everyone. So my name is Lauren, and today I would like to do two things. So first, I'm going to provide an update on the Glitter software that we are using for LA ICP-MS data processing. And second, I would like to show you some of the great developments that we're doing in our lab working on in situ rubidium strontium techniques. So I am the most recent addition to the Glitter team here at Macquarie. My role is partly working on software development, but mostly focusing on the development of a documentation for the new release that will come out in January 2021. So a few of the features that will be released include, but aren't limited to, ratio plots, enhanced sample and standard search functions, the integration of PA factors in and plotting, and segmented external calibration modeling. So now I would like to go on to the rubidium strontium stuff that we've been doing. The rubidium strontium isotopic system is among the most commonly used dating techniques in the earth sciences. And a large reason for this is that rubidium and strontium are very abundant in lithospheric and extraterrestrial materials. And although somewhat regarded as a downfall of this technique, rubidium strontium are very fluid mobile. And in comparison to other dating systems, such as uranium-lead in, say, Zircons or rutiles, rubidium strontium in, say, for example, biotite has a much lower closure temperature. And this makes the age signature susceptible to resetting. But because of this, we are able to gain more information about multiple alteration events and more petrographic information pertaining to the post-alteration processes. One of the largest limitations of the rubidium strontium isotopic method is the isobaric overlap of 87 rubidium and 87 strontium. And so conventionally, the way we've overcome this is using wet chemistry methods, but this is extremely time consuming. And most importantly, when you do wet chemistry methods, you turn your sample into a powder and digest it. So you erase all the spatially relevant information contained in the sample. However, now with the newly developed triple quadrupole ICP-MS, we have a much more controlled approach to mass spectrometry. So we can filter our masses before and after a reaction cell, and we can react, say, for example, our strontium away from our rubidium. So here at Macquarie, we've actually made significant progress on this new technique, and we've recently published a paper where we explored various laser and mass spectrometer parameters. And the work that we're producing it has come a long way, and it's become a routine method in our labs. So now I would like to go through a few examples of this technique. The first one is a thin section sample from Port Macquarie. It's an eclogite. And so we analysed phengite, glaucophane, and lawsonite mineral phases. And what we found is that it produced 2 isochrons, giving us 2 ages and 2 initial strontium ratios. And paired with the XRF and the EDS mapping, we were able to expose not only the age in which this rock forms, but further alteration ages from when this rock was altered. And this is something that previously with conventional rubidium strontium analysis, we couldn't really obtain. But now using in situ techniques, we can get so much more information from the samples we're analyzing. So here's just a few more examples that I won't spend too much time going through, but just briefly, I would like to demonstrate the versatility of this method and the range of ages and the samples that we can analyze using this technique. So the first one on the left is a sedimentary sample located in the Flinders Ranges from South Australia. And this sample that was analyzed was a diagenetic glauconite, which is really great that we can do sedimentary samples in situ. In the middle is a magmatic sample from the West Kimberleys, it's a lamproite, and this is a 20 million year age sample. And this is great because this is the youngest sample by far that anybody has been able to analyze using this in situ rubidium strontium technique. And on the right is another magmatic sample that is somewhat old. And all three of these results are well within agreement of previously published ages. And so we're doing really great work here at Macquarie with this technique. So just to summarize, this newly developed in situ rubidium strontium technique provides a new potential to date and track fluid and melt transportation processes that were previously not accessible by conventional rubidium strontium analytical techniques. The abundance of rubidium and strontium in many rock-forming minerals, as well as the ability to rapidly date with high precision, great resolution, with very little sample preparation required for at least as young as 20 million years. This in situ rubidium strontium technique is proving to be a very powerful toolkit added to the earth sciences. So I'd like to thank you all, and I'm going to now pass you back to Olivier, who will finish up our session.
As a closing statement, I will say that this is only a small part of what we do here at Macquarie. And again, I will invite all of you who have a question about a research question, an exploration question, to get in touch with us. And we have a team of skilled geochemists and engineers, which are ready to try to tailor a solution, analytical solution for you.